In the vast silence of the cosmos, a lone traveler drifts farther than anything humanity has ever sent before. It is small, about the size of a compact car, yet it carries with it the voice of an entire civilization. This traveler is Voyager 1, a spacecraft launched nearly half a century ago that now floats more than 15 billion miles from Earth. Against all odds, it still whispers faint messages home, signals that have traveled through an unimaginable gulf of darkness, taking nearly a day to reach us. And if you want to know how we are still in contact with Voyager 1, then watch this video till the end and subscribe to the channel. Let's begin. Voyager 1 began its odyssey on September 5, 1977, launched from Cape Canaveral, Florida, aboard a Titan IIIe rocket. Built by NASA's Jet Propulsion Laboratory, JPL, it was one of two twin spacecraft, Voyager 1 and Voyager 2, sent to explore the outer planets of our solar system. The late 1970s were a golden era for space exploration, and the timing of the Voyager launches was no accident. The planets were aligned in such a rare configuration, an event occurring only once every 176 years, that allowed a single spacecraft to use the gravity of one planet to slingshot to the next. This gravitational dance became the key to the Voyager missions, enabling them to journey beyond Jupiter, Saturn, and eventually toward the edge of our solar system. Voyager 1's trajectory was designed to take it past Jupiter and Saturn faster than its twin. It reached Jupiter in March 1979, capturing breathtaking images of the giant planet's turbulent atmosphere, swirling storms, and its fascinating moons, including volcanic Io and icy Europa. Just a year later, in November 1980, it made a historic encounter with Saturn, revealing intricate details of its majestic rings and discovering new moons such as Prometheus and Pandora. After completing its planetary tour, Voyager 1 was set on a path that carried it upward out of the plane of the solar system, forever leaving behind the gravitational influence of the planets. Now, over 47 years later, Voyager 1 has traveled a mind-bending distance of more than 15 billion miles, around 24 billion kilometers, from Earth. To put that into perspective, light, the fastest thing in the universe, takes over 22 hours to travel from Voyager 1 to Earth. It is the most distant human-made object ever created, still flying onward into the unknown, long past the point where the Sun's magnetic field fades into interstellar space. What began as a short-term mission to study a few planets has evolved into humanity's first step into the galaxy. Voyager 1 has become more than a spacecraft. It is a silent ambassador of Earth, drifting through eternity. After setting the stage for its incredible journey through the solar system, it's important to understand why Voyager 1 was sent out in the first place, what its original purpose truly was. When NASA first envisioned the Voyager program, the mission's goals were bold, clear, and deeply scientific. To explore Jupiter and Saturn, their rings, magnetic fields, and especially their moons. At the time, humanity had never seen these worlds up close. We had only blurry telescope images and scattered data. But Voyager 1 was built to change that. It wasn't designed as an interstellar explorer at first. It was a planetary emissary, a robotic observer, tasked with revealing the outer planets in unprecedented detail. The spacecraft carried with it a sophisticated suite of instruments, cameras, spectrometers, magnetometers, plasma detectors, and cosmic ray sensors, all meticulously engineered to capture the physical and chemical mysteries of the gas giants. Its twin, Voyager 2, was planned to continue on toward Uranus and Neptune, but Voyager 1's primary directive was to dive deep into the gravity wells of Jupiter and Saturn, to record, measure, and beam back knowledge that would reshape our understanding of the solar system. When Voyager 1 approached Jupiter in 1979, It sent home images that stunned the world. It revealed Jupiter not as a simple striped ball of gas, but as a living, dynamic system, its atmosphere a swirling canvas of storms, tempests, and chaotic beauty. The spacecraft's cameras captured the first detailed images of Eo's volcanic eruptions, the first active volcanoes ever seen beyond Earth. It showed Europa's icy surface, hinting at the possibility of a hidden ocean beneath. For the first time, scientists had direct evidence that other worlds could harbor the ingredients for life. Then came Saturn, with its breathtaking rings and mysterious moons. Voyager 1's encounter with Saturn in 1980 was equally historic. It uncovered the complex structure of the planet's rings, revealing that they were not solid, but composed of countless particles, each following its own orbit, like a vast celestial orchestra. It also discovered intricate ringlets, spokes, and gaps that hinted at gravitational influences from hidden moons. Voyager 1 passed by Titan, Saturn's largest moon, and discovered a thick nitrogen atmosphere, something never before observed outside Earth. This single finding would later inspire future missions like Cassini-Huygens to explore Titan in greater depth. Yet, after its encounter with Saturn, Voyager 1's story took an unexpected and poetic turn. Rather than being shut down or left adrift in the void, it was given a new mission, the Voyager interstellar mission. Its task: to keep traveling outward, to leave the influence of the Sun's magnetic bubble, and to enter interstellar space. No spacecraft had ever done such a thing. As it ventured farther, it continued measuring the solar wind, cosmic rays, and magnetic fields, helping scientists define the boundaries of our solar system, a region known as the heliosphere. This transition from a planetary mission to an interstellar one marked a turning point in human history. Voyager 1 was no longer just a visitor to planets. It had become a pioneer of the galaxy, humanity's first messenger to the stars. Its purpose had evolved from exploration to endurance, from discovery to legacy. And as it crossed that invisible frontier in August 2012, entering interstellar space, it confirmed that the Sun's influence does indeed end, and that beyond it lies the endless ocean of the Milky Way. Voyager 1's original mission had concluded decades earlier, but its journey was far from over. It had transformed from a scientific instrument into a living story, one of persistence, curiosity, and the unyielding human desire to know what lies beyond. Now, nearly 5 decades after it first left our planet, Voyager 1 has ventured into a place no human-made object has ever gone before. It currently drifts more than 15 billion miles, or roughly 24 billion kilometers, from Earth. At that distance, our Sun is no longer a dominant presence. It has faded to a bright star among countless others. Voyager 1 has left behind the solar wind and the protective magnetic cocoon known as the heliosphere, entering what scientists call the interstellar medium, the vast expanse of space that lies between the stars. The interstellar medium isn't empty, though it's almost unimaginably sparse. It's a thin soup of gas, dust, and charged particles, remnants of ancient stars that exploded long ago. Voyager 1 is traveling through this delicate sea of atoms and cosmic rays, gathering data that helps scientists understand what truly exists beyond the reach of our Sun. The spacecraft has become our only direct witness to this mysterious region. Every piece of information it sends back offers clues about how the Sun interacts with its galactic neighborhood and how the boundaries of our solar system are shaped. At its current speed of about 38,000 miles per hour, over 61,000 kilometers per hour, Voyager 1 continues to move steadily away from Earth. Each day, it puts another million miles between itself and the world that built it. Yet even at this extraordinary velocity, it would still take more than 70,000 years to reach the nearest star, Proxima Centauri. That's how staggeringly vast interstellar space is, a realm where distances are measured not in miles or kilometers, but in light years. Out there is no gravitational pull from planets to guide it, no solar wind to push it, no sunlight bright enough to power its systems. It travels through cold, near absolute darkness, where temperatures plunge to around minus 454 degrees Fahrenheit, minus 270 degrees Celsius. Its instruments are shielded against cosmic radiation, and its power source, a slowly decaying radioisotope thermoelectric generator, continues to provide just enough energy to keep a few key systems alive. In this desolate frontier, Voyager 1 is utterly alone, separated from everything human by a distance so immense that even light, the universe's fastest traveler, takes almost a full day to bridge the gap. The region Voyager 1 now explores is more than just space beyond the planets. It's the threshold between the solar system and the galaxy itself. Scientists call this area the interstellar boundary region, where the outward pressure of the solar wind finally balances and then gives way to the inward pressure of particles from interstellar space. In 2012, instruments aboard Voyager 1 detected a sharp change in particle density and magnetic fields, confirming what scientists had long hoped for. The probe had crossed into the interstellar medium, officially leaving the Sun's domain. Even from this unimaginable distance, Voyager 1 remains in motion. Not aimlessly, but with quiet purpose. Its path is determined by the same physics that governs all celestial motion, and it will continue moving outward indefinitely, orbiting the center of the Milky Way like a tiny, persistent satellite of humanity. It doesn't head toward any particular star. Instead, it drifts through the galaxy's dark outskirts, carrying with it the data it continues to send, and the message it carries for whoever or whatever may someday find it. Though it's now far beyond the planets, far beyond the influence of the Sun's wind and radiation, Voyager 1 is still, miraculously, in contact with Earth. That faint, ancient signal it sends is a thread connecting us to the unknown, stretching across billions of miles. And that raises the incredible question that captures the heart of Voyager's story. How is it possible that we can still talk to something so far away? The question almost sounds impossible, almost like science fiction. Here we are on a small blue planet, orbiting an average star in the corner of a spiral galaxy. And somewhere out there, more than 15 billion miles away, a fragile machine built by human hands is still speaking to us. It's not shouting through the void, it's whispering, sending the faintest trace of a signal through the endless dark. And somehow, across this vast gulf of emptiness, we hear it. So how is that possible? How can a spacecraft the size of a small car, built in the 1970s with technology far less advanced than a modern smartphone, still hold a two-way conversation with Earth today? When we think about the sheer distance involved, the feat borders on the miraculous. Every second, Voyager 1 moves farther away, so far that by now, the radio signals it transmits take over 22 hours just to reach Earth. By the time those signals arrive, they are unimaginably weak. So faint that if you compared their power to a light bulb, it would be less than a billionth of a watt. It's like trying to detect the glow of a single Christmas light from beyond the orbit of Neptune. Yet somehow, Earth can still pick it up, decode it, and even send messages back that Voyager 1 can understand. That fact alone is astounding, not just scientifically, but philosophically. We are, in a sense, holding a long-distance conversation with a piece of ourselves, flung beyond the solar system, traveling through the void where no sunlight shines and no sound can travel. It's a conversation between human curiosity and the universe itself, one that takes almost 2 days for a single question and answer to complete. This mystery leads us to the heart of the story: communication. The entire connection between Earth and Voyager 1 depends on the invisible threads of radio waves, electromagnetic signals traveling at the speed of light. But even that isn't enough. Those faint signals have to be caught, understood, and turned back into meaningful data. And to do that, we rely on one of the most powerful and sensitive technological systems ever built by humanity, NASA's Deep Space Network. So as we continue unraveling Voyager 1's story, the central question becomes clear, a question that defines the very limits of human ingenuity. How do we still talk to Voyager 1, a spacecraft now more than 15 billion miles away, drifting through interstellar space? At the heart of this extraordinary communication lies one of the simplest yet most powerful forces in the universe: radio waves. Voyager 1 doesn't use lasers, fiber optics, or any form of futuristic data link. It communicates with Earth using the same basic principle that allows us to listen to the radio or use Wi-Fi. The difference is scale. Instead of traveling across a city or a continent, Voyager's radio waves journey across billions of miles of empty space, racing toward Earth at the speed of light, roughly 186,000 miles per second, about 300,000 kilometers per second. When Voyager 1 sends a message, it's not a spoken word or a clear image. It's a stream of binary data, sequences of ones and zeros encoded into radio signals. These signals are transmitted by its high-gain antenna, a large parabolic dish measuring about 3.7 meters, 12 feet, in diameter. This antenna focuses the radio energy into a narrow beam aimed precisely at Earth, ensuring that as much of the signal as possible is directed toward our planet, rather than being lost into the vastness of space. The transmitter aboard Voyager 1 is astonishingly weak by modern standards. It operates at around 20 watts, roughly the same power as a refrigerator light bulb. Yet, by the time that signal reaches Earth, it has spread out across an enormous sphere billions of miles wide. What eventually reaches our planet is unimaginably faint, so weak that it's equivalent to a single snowflake hitting the ground every few seconds in terms of detectable energy. Still, NASA's ground-based antennas are so sensitive that they can pick up that ghostly whisper and transform it back into usable data. The radio waves Voyager 1 sends are part of the electromagnetic spectrum, the same family of waves that includes visible light, X-rays, and microwaves. But unlike visible light, radio waves have much longer wavelengths, which means they can travel across the emptiest parts of space with little interference. They don't require a medium to travel through. They move freely through the vacuum, carrying their encoded messages at light speed. Communication with Voyager 1 operates on two main frequency bands: the S-band, around 2.3 GHz, and the X-band, around 8.4 GHz. The S-band was primarily used in the early days of the mission, while the X-band became the main channel for long-distance communication because it allows for higher data transmission and greater resistance to noise. These frequencies are chosen carefully since space is filled with all sorts of background radiation, and only specific ranges are clear enough for deep space communication. Here's how it works. Voyager 1's onboard computer collects scientific measurements from its instruments, readings of cosmic rays, magnetic fields, and plasma densities. These measurements are converted into digital data, which the spacecraft encodes into radio signals and beams toward Earth. On our planet, enormous radio antennas, part of NASA's Deep Space Network, receive those signals, decode them, and convert them into the scientific data we see. It's a delicate dance between machine and mathematics, physics and patience. The incredible thing is that this communication link is two-way. Earth can send commands to Voyager 1 just as Voyager can send data back. When engineers at NASA's Jet Propulsion Laboratory send an instruction, perhaps to adjust an instrument or recalibrate its antenna, that signal also travels at the speed of light, taking about 22.5 hours to reach the spacecraft. Voyager 1 then executes the command, and almost a full day later, its response returns to Earth. That means a complete exchange. One command and one confirmation takes nearly 45 hours. This delicate, almost poetic communication shows the patience and precision of interstellar engineering. Despite being launched in an age before smartphones, Wi-Fi, or even the internet, Voyager 1 uses fundamental physics. The same principles discovered by scientists like James Clerk Maxwell and Heinrich Hertz in the 19th century, to maintain contact with us across billions of miles. It's a reminder that sometimes the simplest ideas are the most powerful. The same invisible waves that carry music to your car radio are the ones carrying humanity's voice into interstellar space. And at the other end of that faint beam of radio light, Voyager 1 listens and speaks, as if whispering across the cosmic ocean. To understand how we can still talk to Voyager 1 from over 15 billion miles away, we must look back toward Earth, to a remarkable system that acts as humanity's ear and voice in the cosmos. This is NASA's Deep Space Network, or DSN, one of the most extraordinary engineering achievements in history. Without it, Voyager 1's faint radio whispers would be forever lost in the static of the universe. The DSN is not just a collection of antennas, it is an intricate, globally coordinated communication lifeline, a technological bridge between Earth and the farthest reaches of space. The Deep Space Network was established in 1958 during the early days of the space age under NASA's Jet Propulsion Laboratory, JPL. It was designed to maintain contact with missions that traveled beyond Earth's orbit, spacecraft headed for the Moon, Mars, and eventually the outer planets. Over time, as missions ventured farther and farther from home, the DSN evolved into something even more powerful, the only system on Earth capable of hearing signals from spacecraft billions of miles away. Today, it supports dozens of missions simultaneously, including probes orbiting Mars, rovers crawling on its surface, and spacecraft like Voyager 1 traveling through interstellar space. At its core, the DSN is made up of 3 massive communication complexes, strategically placed around the globe so that at least one of them can always maintain contact with a distant spacecraft, no matter how Earth rotates. These complexes are located in Goldstone, California, USA, Madrid, Spain, and Canberra, Australia. Each site sits roughly 120 degrees of longitude apart, allowing continuous coverage of the sky. As Earth turns, the baton of communication passes seamlessly from one station to another, ensuring that even as Voyager 1's position changes relative to our planet, its signal is never lost. Each of these sites houses several giant radio antennas, the largest of which is a 70-meter wide dish, wider than a football field. These massive parabolic dishes are capable of detecting incredibly weak radio signals, amplifying them millions of times over, and then decoding them into data scientists can analyze. To visualize the scale of their task, imagine trying to detect the heat from a candle on the surface of Mars. That's roughly the level of sensitivity the DSN achieves when it listens for Voyager 1. But sensitivity alone isn't enough. These antennas also need to be precisely aligned with the spacecraft they are tracking. Remember, Voyager 1's signal doesn't beam broadly like a flashlight. It's a razor-thin cone that must hit Earth's detectors dead on. The DSN antennas must constantly adjust their angles to track Voyager 1 as both Earth and the spacecraft move through space. The slightest misalignment, even a fraction of a degree, could cause the signal to drift away into the void. Inside each DSN complex, lies a maze of technology designed to handle data processing, timing, and error correction. The incoming radio signals are not like strong, clear transmissions. They arrive as faint, barely distinguishable ripples buried in cosmic noise. These signals are received, digitized, and then cleaned up using powerful algorithms to extract the meaningful data encoded within them. It's a process akin to finding a single drop of water in an ocean. But the DSN does it routinely, every day, without fail. The DSN operates across multiple frequency bands: S-band, X-band, and Ka-band, allowing it to communicate with spacecraft at varying distances and power levels. Voyager 1, being one of the oldest active missions, transmits in the X-band, a frequency chosen for its balance between data rate and resistance to noise. Because the signal from Voyager is so faint when it reaches Earth, weaker than a single atom's vibration, the DSN uses ultra-low noise amplifiers, cooled to near absolute zero, to minimize interference and detect even the tiniest fluctuations in signal strength. What's remarkable about the DSN is not just its technical prowess, but its endurance. The network has evolved alongside humanity's ambitions in space. It has communicated with Pioneer, Voyager, Galileo, Cassini, New Horizons, and countless Mars missions. It even supports missions beyond NASA, assisting agencies like ESA, JAXA, and ISRO when their spacecraft journey into deep space. Over decades, the DSN has quietly worked in the background, maintaining an unbroken chain of contact with machines scattered across the solar system, and now beyond it. The coordination between these DSN stations is an art form in itself. As Voyager 1 moves farther from Earth, its position relative to our planet changes, and so does the direction of its signal. The DSN must predict and adjust for this constantly, recalibrating its antennas to remain perfectly aligned. Each handoff between the stations, from California to Spain to Australia, is carefully timed to ensure there's no interruption in communication. The process is so precise that even the delay caused by Earth's atmosphere or the gravitational bending of radio waves near the Sun must be accounted for in their calculations. One of the DSN's greatest challenges is managing signal delay. As of now, any signal sent from Voyager 1 takes over 22.5 hours to reach Earth. That means the DSN must plan its operations meticulously, anticipating commands and responses nearly a full day in advance. When NASA engineers send an instruction, they won't know if it succeeded until almost 2 days later, the time it takes for Voyager 1 to receive, execute, and confirm the message. This time lag demands extraordinary patience and precision, but the DSN handles it with practiced expertise. The network's control center, located at JPL in Pasadena, California, monitors all communications and coordinates between the global stations. Data received from Voyager 1 arrives at one of the antennas, gets processed and cleaned, then sent to JPL's computers, where scientists decode it into meaningful information, from magnetic field readings to temperature logs. Even the faintest transmission can reveal crucial insights about the interstellar environment Voyager 1 now travels through. It's also worth noting that the DSN isn't only listening, it's talking. Each station can transmit powerful radio signals back toward the spacecraft. These signals are generated by high-power transmitters, often exceeding 20 kilowatts, to ensure that when the message finally reaches Voyager 1, there's still enough strength left for the spacecraft to detect and decode it. This two-way exchange forms the heartbeat of the mission, a fragile but enduring dialogue between Earth and the farthest outpost of human creation. And yet, despite all the sophistication of the DSN, what makes it truly extraordinary isn't just its scale or its sensitivity, it's the symbolism. Those giant antennas scattered across 3 continents aren't just scientific instruments, they're the listening posts of humanity's curiosity. They remind us that even as Voyager 1 speeds into the interstellar void, it is never completely alone. As long as its transmitter still breathes and the DSN's ears remain open, that thread of connection, faint, delayed, but unbroken, continues to tie us to our most distant explorer. In every weak signal captured by those antennas lies proof of something profound. That even across billions of miles, through the noise of the cosmos and the silence of space, the human voice can still be heard. To fully appreciate how we maintain a continuous link with Voyager 1, despite it being more than 15 billion miles away, we have to zoom in on the geographical genius behind the Deep Space Network. Its 3 massive stations, spread across the globe in California, Spain, and Australia, form a perfectly synchronized trio that ensures Earth's rotation never cuts off communication with our far-flung explorers. This strategic placement isn't arbitrary. It's a deliberate design that allows 24-hour coverage of spacecraft traveling through deep space, no matter where they are in the sky. Let's start with the Goldstone Deep Space Communications Complex, nestled in the Mojave Desert of California, USA. This is the original heart of the DSN, built in the late 1950s when NASA first began sending missions beyond Earth's orbit. The location was chosen for its isolation, far from city lights and radio interference, making it an ideal site for detecting faint signals from space. The dry desert air also helps minimize atmospheric distortion. The largest dish here, called DSS-14, is a 70-meter, 230-foot behemoth of steel and precision engineering. Its surface panels are aligned with mind-bending accuracy to within a few millimeters, so that it can reflect even the weakest radio waves directly into its receivers. Goldstone not only communicates with Voyager 1, but has historically supported missions like the Mars rovers, Cassini, and New Horizons on its way to Pluto. Moving eastward across the Atlantic, the second DSN station stands near Madrid, Spain, officially known as the Madrid Deep Space Communications Complex, MDSCC. Located in the hills of Robledo de Chavela, this site mirrors Goldstone's capabilities, with several massive antennas, including its own 70-meter dish. The Madrid complex plays a vital role when Voyager 1 moves out of view from the US. As the Earth rotates, Spain takes over the connection, seamlessly continuing the conversation. The European site also benefits from a relatively quiet radio environment, surrounded by natural barriers that shield it from interference. Interestingly, Spain's DSN station is a symbol of global cooperation. Though operated by NASA, it's staffed by international teams who ensure around-the-clock monitoring of spacecraft billions of miles away. Completing the trio is the Canberra Deep Space Communication Complex, CDSCC, in Tidbinbilla, Australia, situated just outside the capital city of Canberra. This station fills the final gap in Earth's rotation cycle, taking over when both Goldstone and Madrid can no longer see the spacecraft's position in the sky. Like its counterparts, it features several antennas, including a 70-meter dish known as DSS-43, which holds a special distinction. It's the only antenna in the world powerful enough to send commands to Voyager 2, and by extension, capable of communicating with spacecraft at the edge of interstellar space. The Australian site's southern hemisphere location is essential, as it provides visibility to parts of the sky that the northern stations cannot reach. The placement of these 3 DSN complexes, roughly 120 degrees of longitude apart, ensures that as Earth spins on its axis, at least one station always has a direct line of sight to any spacecraft, including Voyager 1. This is crucial because deep space communication requires an uninterrupted link. Losing contact, even for a few minutes, could mean missing valuable data or failing to send critical instructions. As one station's view of the spacecraft dips below the horizon, another station on the other side of the planet takes over the signal in a precisely timed handoff. This coordination happens continuously, creating an invisible, seamless chain of communication that wraps around the entire Earth. Each handover between the stations is a carefully choreographed event. NASA's Jet Propulsion Laboratory, JPL, which manages the DSN, runs a global control center that tracks every spacecraft and synchronizes these transitions down to the second. Data flows from the antennas to JPL through high-speed fiber links, where it's processed, cleaned of background noise, and decoded into usable scientific information. To Voyager 1, this intricate system of handoffs is invisible. All it knows is that somewhere, 15 billion miles away, its faint whisper is still being heard. The DSN stations are not static relics of the past. They've evolved with technology. Over the years, NASA has upgraded their antennas with more sensitive receivers, improved signal processing, and higher frequency transmitters. Goldstone, Madrid, and Canberra all feature multiple antennas of varying sizes: 34 meters, 26 meters, and the massive 70 meters, which can work together in array mode to boost signal strength. This technique allows smaller dishes to combine their signals, effectively acting as one larger antenna. For faint signals like Voyager 1's, every bit of added sensitivity matters. Each site also operates under strict environmental and operational protocols. Because the antennas must detect signals weaker than a trillionth of a watt, even the faintest local interference, like a car engine, cell phone tower, or microwave, can disrupt communication. As a result, DSN stations are often located in designated radio quiet zones, where electronic transmissions are heavily restricted. The environment around the antennas is kept meticulously controlled, and every piece of equipment is designed to minimize noise. Perhaps the most poetic aspect of this global system is how it reflects humanity's unity in exploration. Across 3 continents, teams of engineers and scientists, Americans, Spaniards, and Australians, work together to maintain a conversation with a spacecraft now more than 24 billion kilometers away. Each station watches the sky during its own daylight and night cycles, ensuring that Voyager 1 is never beyond reach. Together, they form a global heartbeat, a rhythm of listening, responding, and relaying across oceans and hemispheres. So when Voyager 1's whisper finally arrives at Earth, after traveling nearly a full day through interstellar darkness, it doesn't land in one place. It arrives into a network that spans the globe, where giant metal ears wait patiently to catch it, decode it, and send its story home. These 3 stations, working in harmony, are what allow us to keep hearing the voice of our most distant traveler, even as it drifts farther from home than any dream once thought possible. When you think about Voyager 1's distance, over 15 billion miles from Earth, it's almost impossible to comprehend that any signal from it could still be heard. The sheer weakness of its transmission defies intuition. What Voyager 1 sends back to us is not a loud broadcast, not even a whisper. It's the faintest possible murmur in the vast, echoing silence of interstellar space. By the time its radio signal reaches Earth, it has spread so thin across billions of miles that its strength has diminished to less than a billionth of a watt, about 10 to the minus 16 watts. That's roughly equivalent to the energy a single snowflake releases when it hits the ground. And yet, somehow, the Deep Space Network can still detect it. To put this in perspective, if you were to stand next to Voyager 1 when it transmits, you'd be receiving a radio signal roughly as strong as that from a standard FM radio station in your city. But stretch that signal across 15 billion miles, and it becomes unimaginably weak, a fading ripple in the cosmic ocean. The challenge isn't just distance, it's dilution. Like ripples spreading from a pebble dropped in water, radio waves weaken as they travel outward, their energy spreading across an ever-growing sphere. By the time they reach Earth, those ripples are so faint they blend almost completely into the natural background noise of the universe. So how can NASA still detect this ghostly whisper? The answer lies in the extraordinary sensitivity and precision of the deep space network's antennas and receivers. These instruments are among the most sensitive radio detectors ever built by humankind, capable of distinguishing Voyager's faint signal from the static hiss of cosmic background radiation, solar activity, and terrestrial interference. The key lies in both the engineering of the antennas and the mathematics used to process the signals. Each DSN antenna, especially the massive 70-meter dishes, acts like a giant ear, collecting and focusing incoming radio waves onto a receiver located at its center. These dishes are so precisely shaped that they can reflect even the most delicate signals without distortion. The radio waves are then amplified using ultra-low noise amplifiers cooled to near absolute zero, about minus 270 degrees Celsius or minus 454 degrees Fahrenheit. At such temperatures, the amplifiers generate almost no internal noise of their own, allowing them to pick out Voyager's signal from the faint cosmic background. The level of sensitivity required to detect Voyager 1's transmissions is staggering. The DSN's receivers can detect signals as weak as 10 to the minus 22 watts. That's 1/10 billionth of 1 billionth of a watt. To visualize that, imagine standing on Earth and detecting the energy from a single Christmas light bulb shining on Jupiter, and not just detecting it, but being able to decode the information it carries. This is the level of precision and technological refinement the DSN must maintain every second of every day to keep in touch with Voyager 1. But the process doesn't end with the initial detection. Once the signal is captured, it must be processed, filtered, and decoded. The raw signal that Voyager 1 sends is a stream of electromagnetic waves carrying digital information, sequences of binary code, ones and zeros, that represent everything from scientific data to engineering health reports. However, by the time that data reaches Earth, the signal is so faint and noisy that it's nearly indistinguishable from random static. Advanced signal processing techniques, including correlation, error correction, and frequency analysis, are used to extract meaningful data from that noise. NASA engineers often compare this process to hearing a single drop of rain fall into the ocean and being able to tell what direction it came from. Every photon of that radio signal must be accounted for, its timing precisely measured, and its phase tracked. The DSN's computers perform trillions of calculations to reconstruct Voyager 1's message, turning what would otherwise be a chaotic hum into clear, usable information. One of the most fascinating aspects of this process is that the signal itself is not constant. It varies ever so slightly due to the relative motion of Earth and Voyager 1, a phenomenon known as the Doppler effect. Just as the sound of an ambulance siren changes pitch as it moves past you, Voyager's radio signal subtly shifts in frequency as it speeds away from Earth. Engineers at the DSN must constantly correct for these Doppler shifts, measuring changes as small as a few billionths of a hertz to stay perfectly tuned to the signal. Even a tiny miscalculation could cause the receiver to drift off frequency and lose contact entirely. Despite all these challenges, the DSN doesn't just receive Voyager 1's signal. It also measures it with such precision that scientists can use it to study physics itself. For example, by analyzing the tiny fluctuations in the frequency of the signal, researchers can detect how the spacecraft is affected by interstellar plasma, the thin, charged gas that fills the space between stars. In other words, even the faintness of Voyager's transmission becomes a tool for discovery. The feat of capturing a signal this week is a testament to the DSN's design, but it's also a triumph of human patience and persistence. The people who maintain these systems must constantly fight against nature's interference, solar flares, atmospheric disturbances, even radio interference from our own technology. To protect the integrity of the signal, DSN sites are built in remote, isolated regions and designated as radio quiet zones. In these zones, cell towers, Wi-Fi networks, and other transmitters are heavily restricted. Even the engineers themselves must sometimes work in near silence, electronically speaking, to avoid contaminating the sensitive receivers. Still, perhaps the most poetic aspect of this entire process is the symbolism behind it. That whisper from Voyager 1, weaker than the flicker of a single atom, has traveled for more than 2 decades through the blackness of space, untouched by time or interference. And when it finally reaches Earth, it's caught by a human-made ear that was built precisely for this purpose. Across the darkness of billions of miles, humanity is still listening, and Voyager 1 is still answering. Every faint signal that returns from the edge of the cosmos carries more than scientific data. It carries proof that our curiosity, our ingenuity, and our desire to connect can stretch across the universe itself. Even as its power fades and its instruments grow old, Voyager 1's voice remains, the quiet hum of human achievement echoing in the stars. When we say that Voyager 1 is far away, far doesn't even begin to cover it. The spacecraft is so distant that light, the fastest thing in the universe, takes about 22.5 hours to travel from Voyager 1 to Earth. That means when we receive a signal from it, we're essentially hearing from the past. The data arriving at NASA's antennas right now left the spacecraft almost a full day ago. And when we respond, our message will take another 22.5 hours to reach it. In total, a single round-trip exchange, one message out and one reply back, takes nearly 45 hours, or almost 2 full days. This delay turns every communication with Voyager 1 into an exercise in patience and precision. The process begins at NASA's Jet Propulsion Laboratory, JPL, in Pasadena, California, where engineers and scientists craft specific commands. These could be anything from adjusting an instrument settings to pointing the antenna a fraction of a degree, or even updating software stored in the spacecraft's ancient memory banks. Once the command sequence is ready, it's transmitted to one of the Deep Space Network DSN stations, whichever one currently has Voyager 1 in view. From there, the ground antenna, often one of the massive 70-meter dishes, beams a powerful radio signal toward the spacecraft using its high-frequency X-band transmitter. The message leaves Earth at the speed of light, but despite that incredible velocity, the distance is so vast that the signal must travel more than 24 billion kilometers through interstellar space before reaching its target. During that journey, the signal weakens exponentially, spreading thinner and thinner until it's almost indistinguishable from cosmic noise. Yet Voyager's sensitive receiver can still detect and interpret the command, even though it's a faint whisper from home. When Voyager 1 finally receives the transmission, it processes the command using its onboard computer, a system that would seem primitive today, operating with less memory than a digital wristwatch. But despite its age, this computer remains remarkably reliable. It interprets the binary-coded instructions, carries them out, and, when necessary, sends back a response confirming the action. That reply begins its own 22.5-hour journey back to Earth, retracing the same unimaginable distance across the interstellar gulf. By the time Voyager's message arrives, nearly 2 days have passed since NASA first sent the original command. For modern engineers and scientists used to real-time communication with satellites in low Earth orbit or rovers on Mars, this time delay is both humbling and challenging. It means every decision must be made carefully, every command double-checked before it's sent. There's no room for impulsive corrections or immediate troubleshooting. If a mistake is made, it could take nearly 2 days to find out, and even longer to fix. This delay also changes how engineers think about control. When operating a spacecraft in deep space, you can't fly it the way you might pilot a drone or maneuver a rover on Mars. Instead, Voyager 1 is more like a distant robotic colleague, following pre-programmed instructions and reporting back after long silent stretches. The engineers at JPL often describe it as flying blind in slow motion. Every move, every adjustment, every experiment is planned weeks or even months in advance. The spacecraft must be smart enough, within the limits of 1970s technology, to carry out its instructions autonomously until the next set of commands arrives. To maintain this delicate dance of communication, NASA must also account for the relative motion of Earth and Voyager 1. Both are moving, Earth spinning on its axis and orbiting the Sun, while Voyager continues speeding outward at nearly 17 kilometers per second, about 38,000 miles per hour. The DSN's computers calculate the exact trajectory and timing needed so that when a command is sent, it will arrive at Voyager's precise future position 22.5 hours later. Even the gravitational influence of planets and the bending of radio waves by the Sun's corona are factored into these calculations to ensure pinpoint accuracy. Once the data Voyager sends finally arrives at one of the DSN stations, it's captured by the massive antennas, amplified, and relayed back to JPL for decoding. The signal is so faint by this point, a fraction of a trillionth of a watt, that powerful computers are needed to extract the data from background noise. The information might include measurements of cosmic rays, plasma waves, magnetic fields, or simply housekeeping data reporting the health and status of the spacecraft. It's all carefully analyzed and archived, forming a continuous scientific log of humanity's first voyage through interstellar space. Even the structure of the data transmission itself is a marvel. Voyager 1 doesn't send data in a constant stream like a modern broadband connection. It transmits packets of information, each carefully encoded and error-checked. These packets can contain anything from raw instrument readings to images, back when it was still taking photos in the early part of its mission. Because of the weak signal and immense distance, data must be sent slowly to avoid errors. But more on that when we discuss its transmission speed later. The communication process also requires coordination between multiple DSN sites. Since Voyager 1's position in the sky changes as Earth rotates, one DSN station may begin receiving the signal, then hand it off to another station hours later. This handoff must happen seamlessly, or data could be lost. Around-the-clock teams monitor the process to ensure Voyager's voice is never dropped. Despite all the complexity, there's something deeply poetic about it. Every transmission between Voyager 1 and Earth is like a long-distance heartbeat, a pulse of information crossing billions of miles. When NASA sends a message, it's an act of faith, a promise cast into the darkness that, nearly 2 days later, an answer will come. And so far, it always has. The sheer patience required to maintain this connection speaks volumes about humanity's persistence. For nearly half a century, engineers have been sending instructions to a machine that's now beyond the reach of sunlight, trusting that it will still be there, still listening. And each time its faint reply arrives, 22.5 hours later, it's proof that we're not just reaching into the cosmos is answering back. When you think about communication in today's world, instant video calls, lightning-fast downloads, and high-speed internet, Voyager 1's data transmission seems almost impossibly slow. In fact, it's not just slow by modern standards. It's slower than the earliest dial-up connections from the 1990s by many orders of magnitude. Voyager 1 currently sends data back to Earth at a rate of about 160 bits per second, and sometimes even slower, depending on how much power is available and the alignment of the spacecraft. That's not kilobits, not megabits, just bits. To put that into perspective, 160 bits per second is roughly equivalent to transferring a single character of text every 50 milliseconds. It would take more than 10 hours just to send a single low-resolution image from the spacecraft. But for Voyager 1's mission, that's more than enough. Its instruments no longer need to send high-resolution photographs like they did during the flybys of Jupiter and Saturn decades ago. Instead, it transmits streams of scientific and engineering data, measurements of magnetic fields, cosmic rays, plasma densities, and the health of its onboard systems. These are tiny packets of numerical data, far smaller than the kind of information needed for images or audio. Even though the flow of information is minuscule, every bit counts. Each one tells scientists something new about the unseen frontier Voyager 1 is now exploring: interstellar space. This slow transmission rate is partly a limitation of technology, but it's also dictated by the realities of deep space communication. The signal has to travel more than 24 billion kilometers before it reaches Earth. Over such vast distances, even a tiny amount of background noise can corrupt the signal. To ensure accuracy, NASA sacrifices speed for reliability, using robust error correction codes that protect the data from being lost or distorted. These codes work by sending redundant information along with the original data, allowing computers on Earth to reconstruct any missing bits when the signal finally arrives. It's a bit like repeating yourself when you're talking on a bad phone line, just to make sure you're understood. Back when Voyager 1 was launched in 1977, the spacecraft could transmit data at much higher speeds, up to 115,200 bits per second when it was near Jupiter. The signal was strong then, only a few hundred million miles from Earth, and the DSN antennas didn't have to work nearly as hard to pick it up. But as Voyager continued to travel outward, its signal grew weaker and weaker, forcing NASA to lower the data rate to maintain a stable connection. Each reduction in speed was a trade-off: slower communication, but a clearer and more reliable signal. By the time it reached Saturn in 1980, the rate had dropped to 7,200 bits per second. Once it crossed into interstellar space decades later, it slowed to just a few hundred bits per second, and now hovering near 160. What's truly remarkable is that even at this glacial pace, Voyager 1 still manages to send useful information every day. The spacecraft's digital tape recorder, an onboard memory device, stores data collected from its instruments and transmits it when Earth's antennas are ready to receive. The system is designed to prioritize information. Scientific readings get top priority, while engineering or housekeeping data, like temperatures, voltages, and power levels, are sent less frequently. This careful scheduling ensures that every precious bit transmitted is meaningful. The engineers at NASA's Jet Propulsion Laboratory must also carefully allocate bandwidth between multiple spacecraft, since the DSN is shared among dozens of missions at any given time. Voyager 1 gets scheduled listening windows, specific time slots, when the network focuses on it exclusively. During these windows, data is streamed continuously, faint, slow, and steady, like a heartbeat echoing across the stars. When the transmission ends, the DSN shifts to another spacecraft, perhaps one orbiting Mars or en route to Jupiter. The slow speed of Voyager's transmissions also adds a poetic dimension to its story. In an age where we expect instant communication, Voyager 1 reminds us of a different kind of dialogue, one rooted in patience and reverence. Each bit of data takes almost a full day to reach us, and every sequence of numbers represents hours of travel through the interstellar void. What comes through isn't just scientific data. It's a signal of endurance, proof that a 1970s-era machine is still alive, still functioning, and still reaching back across billions of miles to whisper what it sees. Despite the slow rate, the accuracy of Voyager's transmissions is astonishing. The DSN's ultra-sensitive receivers can detect and decode signals with a signal-to-noise ratio so low that, to human ears, it would sound indistinguishable from static. The data stream is so faint that it must be integrated, added up, over long periods to separate it from background noise. It's a process that requires both advanced technology and human patience, blending modern computing with a kind of cosmic listening art. Another key factor in managing such a slow and fragile data link is the spacecraft's antenna orientation. Voyager's high-gain dish must be pointed with extraordinary precision toward Earth for communication to work. Even a tiny misalignment, as small as 0.5 degrees, could cause the signal to fade beyond detectability. To keep the antenna locked on target, Voyager 1 uses its onboard gyroscopes and small hydrazine thrusters to make subtle adjustments, ensuring that its narrow beam continues to hit Earth dead on. The moment that beam drifts even slightly off course, the already weak signal could vanish into the cosmic background forever. There's also a kind of elegance in the simplicity of what Voyager 1 sends. Each bit of data, though small, carries immense scientific value. From these faint transmissions, NASA has learned about the density of interstellar plasma, the behavior of cosmic rays beyond the heliosphere, and the strength of magnetic fields in the galactic environment. In other words, even though the data rate is slower than a human heartbeat, what it delivers reshapes our understanding of the universe. When you look at it that way, Voyager 1 is not just a spacecraft, it's a symbol of perseverance. It's proof that communication doesn't have to be fast to be meaningful. In a universe where distance is measured in light years and time spans across millennia, Voyager's slow, steady voice feels right, like the natural rhythm of space itself. Every faint packet of data it sends is a message across eternity. I'm still here, I'm still listening, and I still have something to tell you. After considering how slowly Voyager 1 speaks to us, sending just a few bits of data per second across billions of miles, it's natural to wonder how this tiny spacecraft still has the energy to speak at all. Nearly half a century after its launch, how can it possibly keep its instruments alive, its transmitter running, and its antenna aimed precisely at Earth when it's so far from the sun that sunlight is weaker than the dimmest glow of a candle? The answer lies in one of the most remarkable technologies ever developed for long-duration space missions, the radioisotope thermoelectric generator, or RTG, Voyager 1's beating heart. Unlike most spacecraft that rely on solar panels for power, Voyager 1 couldn't use sunlight. Once it ventured beyond the orbit of Jupiter, sunlight would be too weak to generate sufficient electricity. Solar panels simply wouldn't work in the cold, dim regions of the outer solar system, let alone in interstellar space. So engineers at NASA's Jet Propulsion Laboratory had to find a power source that didn't depend on the sun, one that could last for decades, be utterly reliable, and require no maintenance. Their solution was to harness the steady, natural decay of a radioactive element, plutonium-238. Voyager 1 carries 3 multi-100-watt radioisotope thermoelectric generators, MHWRTGS, mounted on a long boom extending from the spacecraft's main body. This design keeps the radioactive material safely away from the sensitive scientific instruments and electronics. Each RTG contains about 24 pounds, roughly 11 kilograms, of plutonium dioxide, PuO2, which undergoes radioactive decay, a process that releases a continuous flow of heat as the plutonium atoms spontaneously break apart. This decay is completely natural and predictable, producing no explosions or chain reactions, just steady warmth, much like the glow of embers long after a fire has burned down. Inside the RTG, this heat is converted directly into electricity using thermocouples, solid-state devices that exploit a simple physical principle known as the Seebeck effect. When two different metals are joined together and there's a temperature difference between their ends, an electric voltage is generated. The hot side of the thermocouple is heated by the plutonium's decay, while the cold side is exposed to the frigid vacuum of space. This temperature gradient continuously generates a flow of electrons, a small but steady electric current. At the time of launch in 1977, Voyager 1's 3 RTGs produced a combined 470 watts of electrical power, about enough to power a modern household microwave oven. But as the plutonium decays and the thermocouples degrade over time, that power output steadily decreases. Today, nearly 48 years later, the RTGs produce less than 250 watts, roughly half of what they once did. That's less than the power needed to run a standard light bulb. Yet it's enough to keep the spacecraft's vital systems alive and its instruments functioning. NASA engineers have had to become masters of power management to make those dwindling watts count. Over the years, they've carefully shut down non-essential systems one by one. Instruments used during the planetary flybys, like the cameras that took those iconic images of Jupiter and Saturn, were turned off long ago. Even heaters that once kept certain components warm have been powered down, leaving some instruments operating in temperatures far colder than they were designed for. And yet, astonishingly, many of them still work. The spacecraft's core systems, the communications, guidance, and a few scientific instruments are prioritized above all else. Each watt aboard Voyager 1 is precious. Power distribution must be balanced with extraordinary precision. If the RTGs produce even a little less electricity than expected, engineers on Earth must decide which instrument to sacrifice next. This process has been ongoing for decades, with NASA extending the mission's life through careful trade-offs. In 2023, for example, engineers devised a clever modification that redirected backup power from a safety circuit, power that had been idle for decades, to keep Voyager 1's instruments running just a little longer. These creative solutions have become essential to preserving communication with the spacecraft, as its power output continues to decline by about 4 watts per year. The RTGs themselves are marvels of simplicity and resilience. They have no moving parts, which means nothing can jam, freeze, or wear out. They just quietly convert heat into electricity, day after day, year after year. And because the plutonium-238 used in them has a half-life of 87.7 years, it will continue to generate heat for many decades to come. Even after Voyager 1 can no longer communicate with Earth, its RTGs will still be producing warmth as it drifts silently through the interstellar medium, a tiny ember glowing in the endless cold. It's also worth noting that the use of RTGs wasn't unique to Voyager 1. It set a precedent for many future missions. Spacecraft like Cassini, New Horizons, and the Curiosity and Perseverance rovers on Mars all use variations of the same technology. But Voyager's RTGs were among the first of their kind to prove that nuclear-generated electricity could power a spacecraft for decades. They showed that it's possible to build machines capable of surviving not just years, but generations, without ever being refueled or repaired. There's something almost poetic about Voyager 1's power source. In a way, it mirrors humanity itself, drawing life from the slow, steady transformation of matter into energy, persisting against entropy for as long as it can. Even now, billions of miles from home, its RTGs continue to hum softly, radiating both warmth and power into the void. That faint energy is what allows its transmitter to send signals, its sensors to record data, and its tiny thrusters to make occasional adjustments to stay oriented toward Earth. So every time we receive a signal from Voyager 1, every time those few bits of data arrive after traveling 22.5 hours across the darkness, we are also hearing the echo of plutonium atoms decaying, releasing their ancient energy. The spacecraft's quiet endurance, powered by the natural forces of physics, is a reminder that the laws of the universe that once shaped the stars are now fueling humanity's farthest messenger. It's a humbling thought. Somewhere in the black expanse between the stars, a car-sized machine built by humans continues to run on the warmth of a few decaying atoms. And with that faint heat, it speaks across the cosmos. As Voyager 1's radioactive heart continues to dim, the challenge of keeping it alive has become a delicate balancing act, one that requires ingenuity, restraint, and an almost artistic understanding of engineering. Every watt matters now. Each flicker of electricity must be carefully rationed, allocated, and sometimes sacrificed. Over the decades, NASA's engineers have performed what can only be described as power triage, turning off non-essential systems one by one to ensure that Voyager 1 can continue performing its most critical function, communicating with Earth. In the early years of the mission, when Voyager 1's power output was near its peak, energy management was relatively simple. The spacecraft's 3 radioisotope thermoelectric generators, RTGs, produced roughly 470 watts, enough to power all 11 of its scientific instruments, its transmitters, heaters, and guidance systems. Back then, Voyager 1 was a fully functioning laboratory in space, sending back images of Jupiter and Saturn, scanning magnetic fields, analyzing cosmic particles, and operating with all systems active. But as the years passed and the plutonium-238 inside its RTGs decayed, the available power began to drop steadily. By the time it crossed into interstellar space, its energy supply had fallen to less than half of what it once was. The decline wasn't sudden. It was a slow, predictable fade, giving engineers time to adapt. Each year, Voyager 1 loses about 4 watts of electrical power. It's a small number by human standards, but in the context of a spacecraft running on less than 250 watts, that's a serious shortfall. To compensate, NASA's mission team has had to make increasingly tough decisions about which systems to keep running and which to turn off forever. These choices are not made lightly. Every switch-off represents the end of a scientific capability that may never be replicated again. The first systems to be powered down were those no longer needed after Voyager 1 completed its planetary flybys. Once the spacecraft passed Saturn in 1980, the mission's cameras and imaging instruments were shut off. The once busy optical sensors that captured Jupiter's storms and Saturn's rings were darkened, their circuits cold for over 40 years now. Later, as the available power continued to dwindle, other instruments followed: ultraviolet spectrometers, infrared detectors, and certain plasma analyzers. What remains today are the core instruments that provide data on the interstellar environment: the magnetometer, the cosmic ray subsystem, the plasma wave instrument, and the low-energy charged particle detector. These are the tools still helping us understand what lies beyond the sun's influence. But conserving energy isn't just about turning off instruments. It's also about maintaining the delicate balance of heat, stability, and communication. The RTGs not only produce electricity, but also heat, an unintended yet vital byproduct. As their power output decreases, they produce less heat, which means the spacecraft gets colder. Some components now operate in temperatures far below their design limits, dipping below -60 degrees Celsius, -76 degrees Fahrenheit. Many of these systems were never meant to function in such conditions, yet they do, a testament to the craftsmanship of 1970s engineering. To manage power in these freezing conditions, engineers have also had to make tough calls about heating elements. Voyager 1 contains several small electrical heaters designed to keep its instruments from freezing. Over time, most of these heaters have been switched off to conserve energy, leaving only the ones protecting the most vital electronics. Some instruments are now colder than the limits specified by their original blueprints, and yet remarkably, they continue to operate. The magnetometer, for instance, has been functioning well below its minimum rated temperature for years, defying expectations. The spacecraft's computer systems and transmitters also demand careful attention. Voyager 1's data transmitter consumes a significant portion of the remaining power budget, and it must remain active at all times if communication is to continue. To reduce its power draw, engineers have fine-tuned the transmitter's output and adjusted how often data is sent. They've also streamlined the spacecraft's software routines to reduce unnecessary processing, conserving precious electricity. Every subsystem operates on strict schedules. Instruments are cycled on and off at specific times to prevent power spikes. In 2019, engineers pulled off one of the most remarkable feats of power management in the mission's history. They discovered a way to reroute electrical current from a safety circuit, a small voltage regulator that protected against surges, to power one of the science instruments instead. That circuit had not been used in decades, yet the modification allowed NASA to extend Voyager 1's scientific life without jeopardizing its safety. It was a bold, creative move, the kind that only experience and deep familiarity with the spacecraft could make possible. Even communication itself is now subject to power budgeting. The spacecraft's digital tape recorder, which once stored data for transmission during peak operations, is only used when absolutely necessary. And the strength of its radio signal, though unwavering in frequency, has been carefully calibrated to conserve every fraction of a watt. The Deep Space Network's massive antennas do the heavy lifting on Earth, amplifying and interpreting Voyager's whisper of a signal. Behind these power decisions is a small team of engineers and scientists who have worked with Voyager for decades. Many of them have spent entire careers learning the quirks and limits of this aging spacecraft. To them, managing Voyager 1's dwindling power is not just a technical challenge, it's a form of stewardship. They are caretakers of one of humanity's greatest achievements, coaxing an elderly explorer to keep speaking just a little longer, to send back one more data point, one more reading from the edge of the sun's influence. NASA estimates that by around 2030, Voyager 1's RTGs will no longer produce enough power to keep even a single scientific instrument running. Long before that, systems will continue to be turned off one by one until only the communication hardware remains. A silent sentinel, still listening for commands that will one day never come. Eventually, even that faint heartbeat will fade as the last watts of power drain away, and Voyager 1 will fall silent. But for now, it endures. Each adjustment, each carefully timed power cut, each creative workaround keeps the spacecraft alive. It is not just a triumph of engineering, but of dedication. A half-century-long act of faith in humanity's ability to stretch its reach across space and time. As long as a single instrument is powered, as long as one signal still escapes into the void, Voyager 1 remains the voice of Earth. Soft, distant, but determined to be heard. As Voyager 1's engineers carefully manage its dwindling power, ensuring every system that remains active counts, another equally vital task continues in tandem: keeping the spacecraft's antenna perfectly aimed at Earth. Because even with power to transmit, communication would be impossible if the signal isn't sent in exactly the right direction. At a distance of 15 billion miles, precision is everything. Voyager 1's high-gain antenna, that 12-foot wide white dish mounted at the front of the spacecraft, must be oriented so precisely that even a tiny deviation could cause its faint signal to miss Earth completely. Maintaining that alignment is one of the most remarkable feats of spacecraft navigation ever achieved. Voyager 1's high-gain antenna, HGA, is its only means of communication with Earth. It's designed to focus radio waves into an incredibly narrow beam, a tight cone less than a degree wide. This beam must be aimed with such accuracy that from Voyager's current position, even a pointing error of 1/10 of a degree would send the signal sailing past Earth by millions of miles. Imagine standing in Los Angeles and trying to shine a laser pointer at a coin sitting in New York, while both you and the coin are moving through space. That's the challenge NASA faces every day in maintaining Voyager's communication link. To achieve this extraordinary precision, Voyager 1 relies on a combination of gyroscopes, celestial sensors, and tiny hydrazine thrusters that allow it to adjust its orientation, or attitude, in three-dimensional space. These systems work together to ensure that the spacecraft's antenna remains locked on Earth's ever-shifting position as both Voyager and our planet move through the cosmos. The spacecraft uses a type of navigation known as three-axis stabilization. Instead of spinning like earlier spacecraft, which used rotation to maintain stability, Voyager 1 holds itself steady, constantly monitoring its position relative to known stars. The onboard star tracker, essentially a space-based camera that recognizes constellations, helps it determine which way it's facing. It compares the observed positions of bright stars with a stored star map in its computer memory. If there's even the slightest deviation, Voyager 1 can detect it. When the spacecraft senses that it has drifted off alignment, it uses its attitude control system, ACS, to make small corrections. The ACS consists of 8 miniature thrusters, each about the size of a finger, which release short controlled bursts of hydrazine fuel. These pulses are incredibly brief, sometimes just a few milliseconds, but they're enough to gently nudge the spacecraft back into its proper orientation. Because there's no air in space to slow motion, these tiny adjustments can have lasting effects. Each burst must therefore be calculated with extreme care to prevent overcorrection. Over the decades, Voyager 1's thrusters have performed tens of thousands of these small maneuvers, keeping its antenna precisely aimed at Earth. The spacecraft's inertial reference units, its internal gyroscopes, help measure how much it rotates with each thruster pulse, allowing engineers to model and predict its motion. The entire system is a graceful, mechanical ballet of precision physics, executed millions of miles from human reach. But maintaining this accuracy hasn't been easy. The thrusters, like every other part of the spacecraft, have aged. They were designed for a mission that was expected to last about 5 years, not 50. Over time, residue from the hydrazine fuel built up in the thruster lines, making them less efficient. By 2017, engineers noticed that the primary thrusters, the attitude control thrusters, ACTS, were degrading. Firing them required longer pulses to achieve the same effect, which meant more fuel use and greater risk of system strain. In a remarkable act of problem-solving, NASA engineers devised a plan to switch to an alternate set of thrusters that hadn't been used since 1980, back when Voyager 1 flew by Saturn. These backup thrusters, known as the Trajectory Correction Maneuver, TCM thrusters, had been dormant for nearly 37 years. No one knew if they would still work. But when NASA sent the command in late 2017, after a 22.5-hour wait for it to reach the spacecraft, the response came back almost 2 days later. The ancient thrusters had fired perfectly. That success gave Voyager 1 a new lease on life. Using the TCM thrusters for attitude control reduced strain on the original set and conserved fuel, extending the mission's duration by several more years. It was one of those rare, triumphant moments in space exploration, a moment where experience, creativity, and persistence overcame the limits of time and technology. Voyager 1 carries only a finite amount of hydrazine fuel, roughly 100 kilograms at launch, with only a small portion remaining today. Engineers estimate that, if used sparingly, this fuel could last until the late 2030s. Once it runs out, the spacecraft will no longer be able to control its orientation. Its antenna will gradually drift away from its precise alignment with Earth, and communication will eventually fade into silence. For now, though, the alignment remains astonishingly accurate. Even from 24 billion kilometers away, Voyager 1's signal still arrives on target, hitting the Deep Space Network's antennas exactly where expected. It's an invisible thread of precision, a direct line through the darkness, maintained by thrusters smaller than your hand, operated by a team of engineers who must wait nearly 2 days to see if each adjustment worked. The process is humbling. Every course correction, every careful thruster pulse, reminds us how fragile and yet how powerful this connection truly is. Voyager 1, the size of a small car, is flying through a cosmic ocean with its antenna always turned homeward, a constant act of faith and engineering that ensures its whisper still reaches us. And as that whisper continues, encoded in faint radio waves that cross the stars, it carries not only data, but the human story itself, a message sent across time and distance, always aimed toward the little blue planet it left behind. As Voyager 1 keeps its antenna perfectly locked on Earth, sending its faint signal across the unfathomable gulf of interstellar space, another layer of complexity unfolds, the actual language of that communication. It's one thing to transmit a radio wave across 15 billion miles, but it's another entirely to encode meaningful information into that wave, ensure it survives its cosmic journey intact, and then decode it back into usable data once it finally reaches Earth. That's where one of the most extraordinary achievements of human engineering takes place: the encoding and decoding of Voyager 1's signals. The process that transforms faint pulses of electromagnetic energy into words, numbers, and discoveries. When Voyager 1 talks, it doesn't send sound, pictures, or even text in the way we think of communication. Instead, it transmits radio waves, oscillating electromagnetic fields that can be modified or modulated to carry information. The spacecraft uses a form of modulation known as phase modulation, where it slightly shifts the phase, the timing of the wave's oscillations, to represent digital data, the binary language of ones and zeros. These ones and zeros are the foundation of everything Voyager sends: scientific readings, system status reports, and even the tiny handshake signals confirming that a command from Earth has been received. Inside Voyager's communication system is a telemetry modulation unit, TMU, a crucial piece of hardware that takes the raw data from the spacecraft's instruments and converts it into this digital stream. The TMU packages the information into small groups known as frames, each containing a precise sequence of bits. These frames are then combined into a continuous stream and overlaid onto the carrier radio wave generated by the spacecraft's radio transmitter. Once modulated, the wave is amplified and sent through the high-gain antenna, beginning its 22.5-hour journey toward Earth at the speed of light. The type of data Voyager 1 sends depends on what the spacecraft is doing. Most of the time, it's transmitting scientific telemetry, information from instruments measuring cosmic rays, magnetic fields, plasma waves, and charged particles. Other times, it sends engineering telemetry, vital data about the spacecraft's health, such as power levels, temperatures, and the status of its systems. Each data packet is carefully labeled with identifying bits so NASA can distinguish one type of information from another once it's received. By the time that signal finally arrives at Earth, however, it's unimaginably weak, a whisper more than 20 billion kilometers away. To detect and decode it, NASA's Deep Space Network (DSN) antennas perform a feat that's part physics, part mathematics, and part pure perseverance. The DSN's massive dishes collect Voyager's radio wave, amplifying it through ultra-sensitive, cryogenically cooled receivers. Then, powerful computers begin the painstaking process of demodulation, reversing the modulation that Voyager applied to its radio signal. In simple terms, demodulation means turning the radio wave back into a stream of ones and zeros. But because the signal is buried in noise, this isn't a straightforward task. The DSN's receivers use error correction codes, mathematical patterns that were built into the signal before it left Voyager. These codes, specifically Reed-Solomon and convolutional encoding, act like a digital safety net. Even if parts of the signal are lost or distorted during transmission, the redundant information embedded within the data allows the computers to reconstruct the missing pieces. It's a bit like reading a book where some letters have been smudged, but because you understand the language and the structure, you can still figure out the missing words. Once the binary data has been fully recovered, it's sent from the DSN antenna to NASA's Jet Propulsion Laboratory, JPL, for decoding and interpretation. There, specialized software translates the bitstream into meaningful telemetry, numerical values that correspond to instrument readings, voltages, temperatures, or signal strengths. For example, a series of bits might represent the magnetic field strength at Voyager's location, while another sequence could indicate the current temperature of its power system. These numbers are then converted into human-readable data, plotted on graphs, and analyzed by scientists around the world. This process of encoding, transmitting, and decoding is a continuous cycle, a delicate conversation happening across nearly 15 billion miles. Even the tiniest bit of data can take hours to send, and every transmission must be perfectly timed. To make the most of the limited bandwidth, Voyager 1's team carefully prioritizes which information gets sent. Scientific data always takes precedence, followed by engineering updates. When something unusual happens, like a sudden change in plasma density or an unexpected system glitch, the spacecraft automatically records the data in its digital tape recorder, storing it until Earth requests transmission. The incredible part of this system is that it's all running on 1970s technology, electronics that predate modern microprocessors, built with components you could now fit inside a smartphone's chip. Yet it continues to function with astonishing reliability. The same encoding methods designed almost half a century ago are still performing flawlessly, faithfully carrying data across the void. NASA's engineers occasionally refer to this process as interstellar whispering, because that's exactly what it is. Voyager 1 is whispering its data into the darkness, and the DSN is listening closely enough to hear it. The faintest phase shift in a radio wave, the slightest change in signal strength, carries with it a wealth of knowledge. From those tiny variations, we've learned about the composition of interstellar plasma, the boundaries of the Sun's influence, and the subtle interactions between the solar wind and the galaxy beyond. There's also a deeper poetry in how this communication works. Every 1 and 0 Voyager sends was produced by an electrical pulse generated billions of miles away by a machine powered by the slow decay of plutonium atoms. Those bits are literal fragments of energy transformed into knowledge. Traveling for nearly a day through the vacuum of space, untouched by any medium, to reach the antennas of Earth. It's a direct, physical connection between our world and the interstellar unknown, a thread of light woven through darkness. In an age of instant communication and endless data, Voyager 1's method is a reminder of the beauty of patience and precision. It doesn't shout into the void, it speaks carefully, steadily, with purpose. And Earth listens, decoding those faint bits of light into understanding, meaning, and wonder. The farther Voyager 1 drifts from home, the more every aspect of its operation becomes an act of patience, prediction, and trust. At a distance of over 15 billion miles, the sheer scale of separation transforms simple engineering tasks into long, nerve-stretching exercises in foresight. What might take seconds to correct on a satellite orbiting Earth can take days when dealing with Voyager 1. The 22.5-hour light time delay each way means that any command sent from NASA must be planned meticulously, checked repeatedly, and then transmitted with complete confidence, because there's no undo button waiting on the other side. When engineers at the Jet Propulsion Laboratory, JPL, issue a command, it's like sending a message in a bottle across an ocean of time. They must anticipate not only how Voyager 1 will receive and interpret the command 22 hours in the future, but also what its condition will be when that message arrives. Will the temperature have dropped enough to change how its circuits behave? Will a cosmic ray have flipped a bit in its memory? Will the signal strength be slightly lower than expected? These are not abstract concerns. They're real, daily questions that define every interaction with humanity's most distant machine. Because of this delay, mission operations unfold at an almost philosophical pace. A single sequence of commands might take days to complete. One day to send, another day to wait for confirmation, and sometimes another to analyze the response. Even small calibration tasks, like adjusting a transmitter frequency or rotating the spacecraft a fraction of a degree, require careful simulation and hours of discussion. The flight controllers at JPL rely on predictive modeling software that can simulate Voyager's future state, including its rotation, temperature, and power output, so that when they send a command, they can be certain it will work when it arrives. This foresight is especially vital because of Voyager 1's age. Launched in 1977, it was built with technology from an era before personal computers, before the internet, before the digital revolution. Its memory is measured in kilobytes, 68 kilobytes to be exact, less than the size of a single email attachment today. Its processors run at speeds that would seem glacial to modern standards. Yet those systems must continue to execute commands, manage power, handle communication, and perform scientific measurements, all autonomously. Engineers can't debug the spacecraft in real time. They must work with a mental model of its inner workings, often relying on incomplete data and decades-old documentation written by people who have long since retired. Then there's the challenge of space itself, a harsh, unpredictable environment that no one can fully anticipate. Beyond the heliosphere, Voyager 1 is constantly bombarded by cosmic rays and high-energy particles that can interfere with its electronics. Every so often, a burst of radiation flips a bit in the spacecraft's computer memory, changing a 1 to a 0 or vice versa. Sometimes, the system automatically corrects the error. Other times, it sends back garbled data that engineers must painstakingly decode. There's no way to shield completely against this cosmic interference. It's part of the price of exploring interstellar space. Compounding these issues is the limited telemetry Voyager 1 can send. With its data rate now down to around 160 bits per second, the flow of information is agonizingly slow. When a problem arises, such as a sudden drop in voltage, an unexpected instrument reading, or a communication anomaly, it can take days to gather enough information to diagnose it. Engineers often have to make decisions with incomplete knowledge, guided by intuition, born from decades of experience. One of the most famous examples of this challenge occurred in 2022, when Voyager 1 began sending back confusing data from its attitude articulation and control system, AACS, the system that controls its orientation. The telemetry indicated that the spacecraft's antenna was misaligned, yet the radio signal arriving at Earth was perfectly steady. Something wasn't adding up. With only fragments of data and a 45-hour round-trip communication delay, NASA's team spent months investigating. Eventually, they discovered that the AACS had started sending its telemetry through the wrong computer, one that had malfunctioned decades earlier. The team rerouted the data flow, restoring normal operations, a feat accomplished without ever physically touching the spacecraft, through nothing but logic, experience, and patience. These moments highlight just how fragile and remarkable Voyager 1's continued survival is. The spacecraft is operating in a region where temperatures hover just a few degrees above absolute zero, where there's no sunlight to power its instruments, and where the faint push of gravity and radiation are its only companions. Every command that reaches it must endure cosmic radiation, solar storms, and the natural decay of its own onboard components. And still, it listens, obeying commands sent from a small blue planet so distant now that the sun itself appears as just another bright star. To keep Voyager 1 functioning under these conditions, NASA's engineers have become part mechanics, part archaeologists, and part philosophers. They dig through ancient documentation written in faded ink, reconstructing long-forgotten schematics to understand how a system was wired or how a circuit was designed. Some of the original engineers who built Voyager now mentor younger scientists who weren't even born when it launched, passing down hard-earned knowledge like oral history. It's a living chain of expertise stretching across generations, sustained by curiosity and respect for this tiny spacecraft that refuses to die. Planning ahead also means planning for the end. NASA knows that someday soon, perhaps in the early 2030s, the spacecraft's power output will no longer be enough to sustain even its most critical systems. Engineers are already discussing how to prioritize the final phase, which instrument should be the last to shut down, and how to preserve the spacecraft's last message for as long as possible. There's a quiet dignity in this process, not desperation, but acceptance. Voyager 1 will not fail suddenly. It will fade gracefully, bit by bit, into silence, just as it has lived, patiently and purposefully. And yet, even now, despite every challenge of distance, time, and technology, that silence has not come. The spacecraft continues to transmit, its faint voice carried across the stars, and Earth continues to listen. It's a relationship unlike any other, a collaboration between machine and humanity stretched across space and decades. Each time a new signal arrives, it's not just data, it's proof of endurance, of persistence, and of connection, a reminder that even from the farthest edge of the sun's reach, we still find a way to be heard. When Voyager 1 left Earth on September 5, 1977, few could have imagined that this small, bus-sized spacecraft would still be operating and sending data home nearly 5 decades later. At the time, NASA's engineers hoped for a mission lasting perhaps 5 years, long enough for the spacecraft to reach Jupiter and Saturn, complete its flybys, and beam back a few hundred images. The idea that it would one day be communicating from interstellar space, more than 15 billion miles away, was a distant dream, something reserved for science fiction. Yet here we are. Nearly half a century later, Voyager 1 is still alive, still powered, and still whispering across the stars. Its longevity has defied every prediction, standing as one of the greatest triumphs of human engineering and endurance in history. The secret to this longevity lies in a combination of robust design, exceptional planning, and an enduring commitment from generations of scientists and engineers. Voyager 1 was built during a golden age of spacecraft construction, when durability and redundancy were prioritized over miniaturization. Every system aboard it, from its transmitters and computers to its scientific instruments, was designed with fail-safes, backups, and physical robustness. Its wiring and circuits were shielded against radiation. Its computer systems were simple, stable, and tested to perfection. In an era before microprocessors, Voyager's computers used hardwired logic and read-only memory, primitive by today's standards, but almost immune to software crashes. Ironically, what now seems outdated turned out to be one of the keys to its resilience. From the beginning, Voyager 1 was over-engineered for survival. Its instruments were built to handle extreme cold, vibration, and radiation exposure. Its systems could withstand wide fluctuations in temperature and voltage. Even its thrusters, tiny nozzles no bigger than a thumb, were built with longevity in mind. And, as proven when NASA reactivated them in 2017, after 37 years of dormancy, they still work flawlessly. The same hydrazine fuel that propelled it during its planetary flybys continues to orient it toward Earth, decades beyond its expected service life. Another crucial factor in Voyager 1's continued success has been careful management and adaptability. Over the years, NASA's mission teams have become masters at extending the life of the spacecraft by prioritizing critical systems, rerouting power, and finding creative solutions to problems no one could have foreseen. Each new generation of engineers has inherited the knowledge of those before them, preserving the spacecraft's legacy through collaboration and ingenuity. When the primary computer began showing its age, they adjusted operating parameters to reduce wear. When the power from its radioisotope generators declined, they shut down instruments and heaters in a slow, deliberate sequence to conserve every remaining watt. Each of these steps extended the mission's lifespan by years, then decades. Voyager 1's longevity also reflects something less tangible, but no less vital: the continuity of human curiosity. Few missions in NASA's history have spanned so many generations. The people who designed Voyager are now elderly or gone, but their work continues through younger scientists and engineers who grew up inspired by its discoveries. They maintain the connection, still sending commands written in software older than they are, still decoding signals that left the spacecraft a day earlier. This intergenerational relay of knowledge and care has kept Voyager 1 alive far beyond any reasonable expectation. The spacecraft's continued operation isn't without struggle. Over time, nearly every part of Voyager 1 has degraded in some way. Its power output has fallen by nearly half since launch. Some of its instruments have stopped functioning, and others operate under conditions far colder than they were designed for. Cosmic radiation has bombarded its electronics for decades, slowly damaging circuits. Yet, remarkably, it endures. Even when its systems behave unpredictably, as when it began sending garbled attitude control data in 2022, NASA's engineers find a way to diagnose and correct the problem from billions of miles away. These victories, however small, are testaments to both the spacecraft's design and the human persistence guiding it. Voyager 1's hardware longevity is matched only by its scientific longevity. It has provided continuous data since 1977, a nearly unbroken stream of information about our solar system and now the space beyond it. Over the decades, it has chronicled the shifting solar wind, the boundary of the heliosphere, and the first direct measurements of interstellar plasma. Its magnetometer and cosmic ray detectors are still collecting vital data, allowing scientists to study the unseen frontier between the Sun's influence and the galaxy's broader environment. Few scientific instruments in history have produced such a long and consistent dataset. When you consider the sheer timescale, Voyager 1's endurance becomes even more astonishing. It has survived through 8 US presidents, countless global events, and technological revolutions that transformed the world. When it launched, computers filled entire rooms. Now, its signal is received by software running on systems millions of times more powerful than its onboard computers. Yet the fundamental process, radio waves traveling at the speed of light, remains unchanged. The same physics that carried its signal home in 1977 carries it still today. There's also a profound symbolic meaning in this endurance. Voyager 1's longevity isn't just about surviving, it's about persistence in the face of the impossible. It represents the enduring human spirit to explore, to ask questions, to reach farther than our lifetimes allow. Each day that its faint signal is detected, it reaffirms something essential about us, that we build not just for today, but for tomorrow, for futures we may never personally see. NASA's current projections suggest that Voyager 1 could continue transmitting until around 2030 to 2035, when its RTGs will finally produce too little power to run its instruments. By then, it will have operated for over 50 years, 10 times longer than its original mission plan. Even after it falls silent, Voyager 1 will not die in the traditional sense. Its systems will simply grow quiet, and it will continue drifting through the galaxy for billions of years. A relic of Earth, a mechanical fossil from a civilization that once looked to the stars and dared to reach them. For now, though, it remains very much alive, still sending back data, still answering when we call. The fact that a machine built by humans in the 1970s continues to function beyond the solar system in 2025 is, by itself, a kind of miracle. Voyager 1 has become not just a scientific instrument, but a timeless monument to perseverance, proof that even the smallest creations of humankind can outlast generations, carrying our curiosity beyond the horizon of time. Over the course of nearly 5 decades, Voyager 1 has transformed from a planetary explorer into a true interstellar pioneer, and in doing so, it has rewritten our understanding of the solar system and the space beyond. Its discoveries have not only deepened our knowledge of the outer planets, but also provided humanity's first direct measurements of the interstellar medium, the vast region that lies between the stars. Voyager 1's journey is not just a tale of endurance, it's a legacy of revelation, a slow unfolding of the universe's secrets through the patient collection of data from a single, aging spacecraft. Voyager 1's scientific contributions began long before it left the Sun's domain. During its planetary encounters in the late 1970s and early 1980s, it forever changed how we viewed the outer solar system. Its flyby of Jupiter in 1979 revealed the planet as a dynamic, violent world filled with swirling storms, immense magnetic fields, and volcanic moons. The discovery of active volcanoes on Io, the first found anywhere beyond Earth, was nothing short of revolutionary. Until then, scientists had believed that small celestial bodies quickly cooled and became geologically dead. Io proved the opposite. Its intense tidal interactions with Jupiter kept it molten inside, reshaping our understanding of how moons and planets evolve. Voyager 1 also exposed Europa's icy surface, crisscrossed with long fractures, hinting at a possible subsurface ocean. That single discovery would inspire generations of planetary scientists and future missions like Europa Clipper decades later. Beyond Europa, the spacecraft sent back the first close-up views of Ganymede and Callisto, revealing them to be complex, ancient worlds with their own histories etched into ice and rock. Each image, each reading, expanded our sense of what the outer solar system could be. Not a static wasteland, but a dynamic, diverse realm teeming with geological activity. Then came Saturn, where Voyager 1 captured the breathtaking intricacy of the planet's rings. Not a simple set of bands, but a delicately structured system of countless ringlets, gaps, and waves shaped by the gravitational influence of moons. It discovered new moons, observed the mysterious spokes in the rings, and, most importantly, conducted the first close study of Titan, Saturn's largest moon. When it found Titan shrouded in a dense, nitrogen-rich atmosphere, scientists realized that this distant world bore intriguing similarities to early Earth, a tantalizing clue about the conditions that may once have fostered life in our own past. But Voyager 1's most profound discoveries came after it left the planets behind, when it turned its instruments outward toward the edge of the solar system. Its mission entered a new phase, to explore the frontier between the Sun's influence and interstellar space. This boundary region, known as the heliosphere, is the vast bubble carved out by the solar wind, the stream of charged particles continuously emitted by the Sun. For decades, scientists theorized about where this boundary might end, but Voyager 1 was the first to cross it and confirm its existence. In August 2012, Voyager 1 made history by becoming the first human-made object to enter interstellar space. The evidence came not from a dramatic visual, but from subtle, quantitative data. Its instruments detected a sudden and permanent increase in cosmic ray intensity and a sharp drop in the presence of solar particles, proving it had left the heliosphere and entered the interstellar medium. This wasn't an empty void, but a region filled with gas, dust, and magnetic fields, the raw material from which new stars are born. One of the key instruments responsible for this discovery was the plasma wave system, PWS. It recorded the vibrations of plasma, ionized gas, in Voyager's surroundings. By analyzing these plasma oscillations, scientists were able to measure the density of interstellar plasma for the first time. To their surprise, they found that interstellar space isn't as empty as once believed. The plasma density was significantly higher than expected, revealing a rich dynamic environment influenced by both the remnants of ancient supernova and the faint breath of our own sun's fading wind. Another vital instrument, the Cosmic Ray Subsystem, CRS, has continued to record the arrival of high-energy particles from distant parts of the galaxy. These cosmic rays carry clues about violent astrophysical processes like supernova explosions and the behavior of galactic magnetic fields. Through Voyager 1's data, scientists have learned how our Sun's protective heliosphere acts as a cosmic shield, blocking many of these energetic particles, and how, beyond that shield, space becomes far more turbulent and alive with radiation. The magnetometer, MAG, has provided equally groundbreaking insights. As Voyager crossed the heliopause, the boundary between the solar wind and interstellar space, its magnetometer detected a subtle but distinct change in magnetic field direction. This confirmed that the spacecraft had indeed entered a new region dominated by the galaxy's magnetic influence rather than the Sun's. The data helped scientists map the structure of this cosmic boundary, showing that the Sun's magnetic field doesn't simply vanish, but blends and twists with the galactic one, forming a complex interface where the two realms meet. Voyager 1 also revealed that this transition isn't a clean, fixed edge, but a porous, shifting frontier. The heliopause breathes, expanding and contracting as solar activity rises and falls. This discovery fundamentally changed how we understand our solar system's boundary. We now know that the Sun's reach extends farther and is more dynamic than anyone had imagined, constantly interacting with the galaxy around it. Perhaps one of the most profound lessons Voyager 1 has taught us is that the interstellar medium is not silent. In 2021, decades after crossing into interstellar space, the spacecraft detected faint, continuous plasma waves, a background hum filling the void between the stars. These waves revealed that interstellar space, far from being dead and still, is a living sea of energy, rippling with the echoes of cosmic events that occurred light years away. Even now, Voyager 1 continues to sample this environment, providing humanity's first long-term study of the space between stars. The spacecraft's measurements have become invaluable not only for astrophysics, but for understanding our place in the cosmos. It has shown us that the Sun's influence, the heliosphere, acts as a kind of cosmic cocoon, protecting Earth and the planets from much of the galaxy's radiation. Understanding the shape and behavior of that bubble helps scientists model how other stars might interact with their own galactic environments, a key insight for studying habitability in other star systems. And while Voyager 1's discoveries are deeply scientific, they also carry an emotional resonance. Every bit of data it sends back is a message from a realm no human has ever visited, a realm no other spacecraft has reached. It has become our eyes and ears in the cosmic wilderness, a lone sentinel drifting through a sea of stars, continuing to teach us about the forces that shape galaxies, planets, and perhaps even life itself. What Voyager 1 has taught us is both humbling and awe-inspiring, that the solar system has boundaries, but curiosity does not. The spacecraft has expanded humanity's physical reach and, perhaps more importantly, our sense of perspective. It has shown us that even in the coldest, darkest reaches of the universe, there is structure, energy, and meaning, and that with enough patience, determination, and imagination, we can uncover it. Among the hum of cosmic rays, the whisper of plasma waves, and the faint heartbeat of its decaying power source, Voyager 1 carries something profoundly human, a message in a bottle cast into the sea of the stars. Tucked on the side of its body, mounted just beneath the long boom that holds its scientific instruments, is one of the most iconic artifacts ever created by humankind, the Golden Record. It is not a scientific instrument, not a sensor or a transmitter, but rather a symbolic gesture, a time capsule, a portrait of Earth, and a testament to the human desire to be known. This confirmed that the spacecraft had indeed entered a new region, dominated by the galaxy's magnetic influence rather than the Sun's. The data helped scientists map the structure of this cosmic boundary, showing that the Sun's magnetic field doesn't simply vanish, but blends and twists with the galactic one, forming a complex interface where the two realms meet. Voyager 1 also revealed that this transition isn't a clean, fixed edge, but a porous, shifting frontier. The heliopause breathes, expanding and contracting as solar activity rises and falls. This discovery fundamentally changed how we understand our solar system's boundary. We now know that the Sun's reach extends farther and is more dynamic than anyone had imagined, constantly interacting with the galaxy around it. Perhaps one of the most profound lessons Voyager 1 has taught us is that the interstellar medium is not silent. In 2021, decades after crossing into interstellar space, the spacecraft detected faint, continuous plasma waves, a background hum filling the void between the stars. These waves revealed that interstellar space, far from being dead and still, is a living sea of energy, rippling with the echoes of cosmic events that occurred light years away. When Voyager 1 and its twin, Voyager 2, were being prepared for launch in the mid-1970s, NASA knew that once they completed their planetary flybys, they would continue outward indefinitely, escaping the gravitational pull of the Sun. That realization sparked an extraordinary idea. If these spacecraft were destined to wander the galaxy forever, why not give them a message from their creators? Why not send something that would represent not just our science, but our humanity, our emotions, our art, our voices, our collective memory as a species? The result was the Golden Record Project, led by a committee chaired by the legendary astronomer and science communicator Carl Sagan. The team included writer Anne Druyan, artist John Lomberg, astronomer Frank Drake, and others who shared a dream of encoding Earth's essence into a form that could be understood by any intelligent life that might someday find Voyager drifting among the stars. Over the course of months, they debated, collected, and curated what would become a phonograph record made of gold-plated copper, designed to last for 1 billion years in the vacuum of space. Each golden record is 12 inches in diameter and contains 90 minutes of audio and 115 images, etched into its surface as analog signals. It's protected by an aluminum cover engraved with symbolic instructions. A cosmic how-to guide explaining how to play it, written in the universal language of physics and mathematics. The cover also includes a diagram showing the location of our Sun relative to 14 pulsars, each identified by their unique frequency, effectively creating a galactic map that any finder could use to trace the record back to Earth's neighborhood. What lies within that golden disk is a symphony of human civilization, a breathtakingly ambitious attempt to capture the diversity of life on Earth. The audio recordings include greetings in 55 languages, from Akkadian, an ancient Mesopotamian tongue, to English, Chinese, and Swahili. There are sounds of nature, the crash of ocean waves, the rustle of leaves, the crackle of fire, the songs of birds and whales, a baby's first cry, a kiss, and laughter. Interwoven with these sounds are pieces of music from across cultures and centuries, Bach and Beethoven, but also Peruvian panpipes, Senegalese percussion, Azerbaijani bagpipes, and a Navajo night chant. It's a tapestry of sound meant to show not just intelligence, but spirit. One of the most touching elements on the record is a recording of brainwaves, those of Anne Druyan herself, captured as she thought about what it means to love, to dream, to exist. In her later reflections, she revealed that during the recording session, she had been thinking of Carl Sagan, whom she had recently fallen in love with. That moment, a human being thinking of love as her brain's electrical whispers were encoded onto the golden record, means that, in a very real sense, Voyager carries the emotion of love itself across the stars. The 115 images encoded in analog form portray the richness of our world. Photographs of people, animals, landscapes, and scientific diagrams. They show DNA molecules, mathematical concepts, and the structure of the solar system. There are images of a mother with her child, a farmer in a rice field, a violinist, and even a page from Isaac Newton's Principia Mathematica. Taken together, these pictures are a gallery of humanity, not perfect, not complete, but genuine. They tell any potential discoverer that Earth is a world of intelligence, creativity, and feeling, a place where beings once looked outward and wondered if anyone else was looking back. Carl Sagan described the golden record as a bottle cast into the cosmic ocean, an act of hope that perhaps one day, somewhere, someone might find it. Yet even if no one ever does, its existence has already fulfilled its purpose. It reminds us that exploration is not just about discovery, but about communication, about the need to reach beyond ourselves and say, "We were here." Voyager 1's golden record is also a poignant juxtaposition of scale and meaning. The spacecraft is a mere speck against the infinite backdrop of the Milky Way, smaller than a grain of dust in the galactic ocean. Yet it carries within it a record of an entire species. That paradox is the essence of Voyager's mission, that something so small, so fragile, can hold something so vast? Over the decades, as Voyager 1 has traveled farther and farther from home, the significance of the golden record has grown deeper. It is no longer just a message to hypothetical extraterrestrials. It has become a message to ourselves. It symbolizes what we value most when stripped of everything else: art, knowledge, connection, and compassion. It's the human story, distilled into sound and image, floating through the interstellar void long after our cities crumble and our sun fades. Even if no alien civilization ever finds Voyager 1, the golden record ensures that a piece of Earth, a piece of us, will exist in the galaxy for billions of years. Long after our species is gone, that little golden disk will continue to spin silently aboard a darkened spacecraft, carrying greetings, music, and the heartbeat of our planet through the stars. Somewhere out there, between suns and nebulae, Voyager 1 continues its voyage, a lone traveler bearing the signature of humanity, our culture compressed into a golden memory, still gliding forward at 38,000 miles per hour. And perhaps that is the greatest message of all, that even in the vast silence of the universe, we have chosen not to remain silent ourselves. Now, nearly half a century after it left our world, Voyager 1 drifts silently through a realm no human eye will ever see. A tiny spark of metal and memory, moving forever outward into the vast dark between the stars. It carries no destination, no guidance but inertia, and yet its journey embodies one of the most profound truths about humanity: that we are compelled to explore, to reach beyond what we know, and to leave a trace of ourselves in the unknown. Voyager 1 is, in the simplest terms, a machine: circuits, wires, fuel lines, and a fading nuclear heart. But it has become something far greater, a mirror in which we see our best qualities reflected: curiosity, perseverance, imagination, and hope. It is the quiet embodiment of our refusal to accept the limits of our horizon. Against all odds, it continues to speak, its faint signal taking nearly a day to cross the gulf of space, still whispering back to the planet that gave it birth. That whisper, weaker than a billionth of a watt, is the most distant voice humanity has ever heard. It's a reminder that our influence, however small, can reach across unimaginable distances. When the Deep Space Network catches that faint signal, what it receives isn't just data, it's a heartbeat, the steady pulse of human achievement echoing across time and space. Voyager's transmissions are the purest form of communication ever made, the voice of an entire species, speaking to the cosmos not in words, but in perseverance. Think about that for a moment. A small probe, built in the 1970s with technology simpler than a pocket calculator, has outlasted every prediction, every limit, every generation of its creators. It has traveled more than 24 billion kilometers from home, crossed the invisible threshold where the sun's influence ends, and entered the great interstellar ocean. There is no sunlight there, no warmth, no sound. And yet, Voyager 1 endures. It continues to turn its antenna toward a tiny, pale blue dot, now lost in the glare of distance, holding its aim with quiet faith that someone is still listening. And we are. Every day, in a laboratory in California, engineers and scientists wait for its signal to arrive. A faint murmur that left Voyager 22.5 hours earlier. They decode its bits, translate its silence into meaning, and in doing so, bridge a distance so immense that light itself grows weary. That act, that listening, is as symbolic as the spacecraft's voyage itself. It says that we, the people of Earth, are still reaching outward, still listening for echoes of our own curiosity in the void. Voyager 1 has become a monument, not of stone or metal, but of motion and endurance. It is a testament to human continuity, carrying with it both science and sentiment. data about the interstellar medium, and the golden record's chorus of voices, music, and dreams. It represents the fusion of intellect and emotion, of logic and longing, proof that our species builds machines not just to survive, but to express something deeper, the need to connect. It's poetic, really, that our farthest creation is not a weapon or a monument of conquest, but a messenger of peace, a record of laughter, art, and music sent into the void. Voyager 1 tells the universe who we are: curious, flawed, hopeful, and endlessly reaching. It carries the sounds of thunder and the hum of crickets, the greetings of countless tongues, and the heartbeat of a species that looked up at the stars and decided to say hello. And someday, long after the last transmission fades, Voyager 1 will continue its journey. Its systems will fall silent, its thrusters will freeze, its antenna will drift off alignment. But the spacecraft itself will keep traveling, orbiting the Milky Way once every 225 million years, circling the galaxy again and again, long after Earth's mountains have eroded and its oceans dried away. It will outlast our civilizations, our languages, and perhaps even our species. For billions of years, Voyager 1 will remain, silent but steadfast, carrying within it the evidence that once, in one corner of the galaxy, life arose, and that life reached for the stars. In this sense, Voyager 1 is not merely a spacecraft, it is a symbol of time itself, of endurance beyond decay, of purpose beyond presence. It reminds us that the things we create in the pursuit of knowledge can outlive us, bearing our fingerprints into eternity. Its voice may be faint, but it speaks volumes. That even from a fragile planet orbiting an ordinary star, something extraordinary can emerge. Carl Sagan, whose vision helped shape the mission, once reflected on Voyager's view of Earth, that famous image of the pale blue dot captured by its camera before it turned away forever. In that photograph, Earth is no more than a speck suspended in a sunbeam. "That's here," Sagan said. "That's home." That's us. Voyager 1 is now far beyond the reach of sunlight, but it carries that same perspective with it, the understanding that our smallness does not diminish our significance. In fact, it magnifies it, because Voyager 1 is ultimately a human story. It's about the engineers who built it, the scientists who guided it, the poets who gave it meaning, and the generations who continue to be inspired by it. It's about the endless interplay between curiosity and courage, about asking questions not because the answers are easy, but because they are hard. It's about looking into the infinite and daring to wonder if someone, somewhere, might be looking back. So, as Voyager 1 sails onward into the dark, silent, solitary, but still bearing the light of human curiosity, it becomes more than a spacecraft. It becomes a metaphor for us all, fragile, fleeting, yet unyielding in our desire to explore, to understand, to leave behind something that says we existed and we cared to know more. And perhaps, billions of years from now, if some distant intelligence ever finds it drifting through the stars, they will learn not just who we were, but what we aspired to be, a species that refused to stop reaching. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.